When we're looking at velocity, there's a difference between an average velocity and an instantaneous velocity. Now we have this common definition of velocity as being the change in position over time. And it's this over time part that's very important to average velocity, that is over a time interval. So when we're finding an average velocity, it's from the beginning of a time period to the end of a time period. So for example, if the height of an object dropped from 100 feet is modeled by the function h of t equals negative 16t squared plus 100, let's find the average velocity on the interval from 0 to 2. So with this dropped object problem, the way this looks graphically is that it starts off at 100 feet. And as time increases, the height keeps getting lower and lower and lower. So when we're talking about the average velocity from 0 to 2, we're looking at its position at time being 0 seconds and time being 2 seconds. Well, we need to know where its position is at that 2-second spot. And we can find that by just plugging 2 into our function h. And what we'll end up with is negative 64 plus 100, so 36. So when we want to find that average velocity from that 0 second to 2 second point, what we're looking at is that average rate of change in the position over that time, which is a slope. So to find that average velocity, what we're going to do is just take its position at 2 minus its position at 0. That's the change in position divided by 2 minus 0, which is the change in time. So when we do our little calculating, we'll have 36 minus 100 over 2. That's negative 64 over 2, which is negative 32 feet per second. So what we see is the average velocity is really slope of a secant line. When we want to do this again from over the interval from 1 to 2, then we're shortening our interval, and so we need to find this point as well and then identify what that slope is. Well, h of 1 is going to be negative 16 plus 100, which is 84. So to find our average velocity over this time period, we'll do the change in position, so 84 minus 100, over the change in time, 1 minus 0. And that'll give us negative 16 feet per second. Now when we're talking about an instantaneous velocity, that's that velocity at a specific point in time. So it's not over an entire interval. What we're end up doing, like the mechanics mathematically, if we want to find the instantaneous velocity at the time being 2 seconds in the same problem, what we're going to do is let this point that started at the origin and now moved over to 1, we're just going to continue to let that x coordinate move closer and closer to that 2, right? Until eventually what we're looking at is the slope of a tangent line instead of the slope of a secant line. And we all know that slope of a tangent line is the derivative. So to find the instantaneous velocity, we have to first find the derivative of h, which is going to be negative 32t. Then we can find the derivative at 2 seconds. And we'll get negative 64 feet per second. Let's take a look at another problem where a diver jumps from a 32-foot tall platform. Her height after t seconds is given by h of t equals negative 16t squared plus 16t plus 32. What's happening in this problem now is that the object is the diver, and she's not just being dropped, she's jumping. So she has some initial velocity where she's going up first before coming down. Now, she's starting off at 32 feet. And we want to know when she hits the water. So when she's down here, when her height is 0. We don't know what that time is, but we do know that the height is, of course, 0. So in order to figure out when she hits the water, we're going to take that function that we're given, h of t, and find out when it equals 0. Now this is really an algebra 2 problem. All we have to do is divide by -16. We'll have t squared minus t minus 2. And then we can factor it. And we see we get 2 solutions, one of them being 2 and one of them being -1. And of course, within the context of this problem, having a time of -1 isn't going to be helpful. So our solution is going to be time equals 2, that being when she hits the ground is at 2 seconds. Now, what's her velocity at impact? So we need to determine, are we looking for an average velocity or an instantaneous velocity? And since it says at impact, we are talking about that instant that she comes in contact with the water. So the instant that she lands, that's an instantaneous velocity. So we need a derivative. Finding the derivative of h would be -32t plus 16. And now we want to know the instant she hits the water, that's going to be at 2 seconds. So h prime of 2. And we get -48. Including the units with this, because we are given units, we know that the position is measured in feet and the time is measured in seconds. That's why we'll have that velocity in feet per second. One thing I haven't talked about yet, but is it normal that we should have a negative velocity? I mean, in the first part, we said we couldn't have a negative time. That's why we crossed it out over here. But can we have a negative velocity? And the answer is yes, because when we're talking about velocity, that is speed with direction. Right? And having a negative velocity just means that when she hits the water, she is going down. That's all. Now, instead of thinking about what happens at the end of the dive, let's think about something that happens in the middle. All right? When does she hit her peak? And what's going to be that maximum height? So we know that that peak is going to happen up here. This has always been an Algebra 2 problem, and because h of t is a parabola, we have lots of techniques for finding the vertex of a parabola in an Algebra 2 sort of way. But let's start looking at it in a calculus sort of way. And the idea here is that when she's at her peak, what's her instantaneous velocity? Think about the path of her dive. Initially, she jumps upwards. Right? When she hits her peak, that's when she stops and turns around and starts to go down. So we went from an increasing instantaneous velocity to decreasing instantaneous velocities. So a positive first derivative to a negative first derivative. That means that that derivative at that peak is going to be 0. And so that's what we need to find, is when is now the derivative of h equal to 0. So we find the derivative first. And we said the derivative function is -32t plus 16. And we're going to set that equals 0. Quickly subtracting 16 and dividing by -32 leaves us with t equals 1/2. Which means that peak is going to happen at 1/2 of a second. One-half second after she starts her dive. What is that maximum height? Well, now we just want to find the height, so finding h of 1/2. and that should leave us with 36. So her maximum height is going to be 36 feet. One last problem that I want to start looking at is I refer to as a particle problem. Oftentimes on the AP exam, you're going to hear about a particle that's moving along the x-axis. In this case, the position of that particle is given by S of t equals t squared minus 2t plus 1. Now, it's very easy to kind of get wrapped up in this problem and what we normally think of functions and all of that to get yourself really confused. For instance, normally when we deal with a function, we can think about it on a coordinate plane where there's an x-axis and a y-axis. But in this case, the particle is only moving along the x-axis, so it's only going back and forth along the x-axis. But I have this function, that usually has an x and a y. Well, in this case, it's actually a t and an s of t. So we don't really want to think about this in terms of our coordinate plane. Right? Let's just kind of think about it in terms of our x-axis and a particle moving along this x-axis. So let's think about, first of all, an interval of just 5 seconds. So for t going from 0 to 5 seconds. All right, where does the particle start? Well, its position is given by s, and initially we're going to be at time 0. So s of 0, we plug it in and we'll get 1, which means on our x-axis, if the origin is right here, our particle is starting at 1 unit to the right of that. Where does it end? So at the end of the interval, that's when time is at 5 seconds. So we need to find s of 5. So 5 squared minus 2 times 5 plus 1, that looks like 16 to me. So it's going to end up way over here at 16. Since we know its beginning and its end, we can find the average velocity without a problem. Right? Just find its change in position, 16 minus 1, over its change in time, 5 minus 0. 15 divided by 5 is 3. As far as units go, we've described time in terms of seconds, so the change in time would be measured in seconds. But the units on an x-axis aren't standard. They aren't feet or centimeters or anything like that. So we would just call them units, which means the units for the average velocity would be in units per second, if you wanted to look at it that way. Now, this just kind of gives us an average velocity. It tells us that on average, our particle is constantly moving to the right at a rate of 3 units per second. But let's take a look at the velocity function. We could create a velocity function. It's just going to be the derivative of the position function. So this will give us instantaneous velocities at every second on the interval. So s prime is going to be 2t minus 2. And let's take a look at some points in particular. For instance, the velocity when it starts. At the beginning, when t is equal to 0, we have an initial velocity of negative 2 units per second. Now, that is kind of important to us because when we were finding the average velocity, we just kind of assumed that it was going to consistently move to the right at 3 units per second. But we see that right off the bat, from the start of this time period, the particle first is moving in a negative direction. It's going to move to the left first. So a good question is, well, when does it stop and turn around to start moving to the right? This particle, if it starts moving to the left, but it's got to end up at 16, at some point it stops, turns around, and moves back over to that 16. So let's find that spot next. That's going to happen when our instantaneous velocity changes from negative to positive. Well, that change from negative to positive is at 0. So we want to find when is the instantaneous velocity equal to 0. Well, I'd be at 2t minus 2 is equal to 0. Or t equals 1 second. So after 1 second, that's when it's going to stop and turn around. So what we found here is that 1 second is when the particle stops and turns around. What I want to know next is, where does that happen? Well, that means I want to know its position. If I'm looking for where it happens, that's its position after 1 second. So plugging that back into our position function, s of t, we got 1 squared minus 2 times 1 plus 1, and that actually looks like 0. So to modify our diagram here, our particle is starting at 1 unit to the right of the origin. It moves to the left over to the origin. It takes 1 second to do that before it stops, turns around, and starts going in the positive direction, ending at 16.